Okay guys, so these are some problems from section 8.2. 8.2 is more of the same thing with using matrices to solve these systems, but we're going to be talking about kind of some special cases and what to do with matrices where it doesn't quite get the ones on the diagonal the way it's supposed to. So I've already typed these into my calculator to save us some time. So I typed the first example as matrix A and the second example as matrix B. Okay, so you can look at these. I just typed them in the way we've been doing for 8.1, right? Same way. So now I'm going to do second matrix. I want, again, to do the reduced row echelon form. And let's do matrix A first, so example 1. And so what happens is the calculator is going to give me its best attempt, right? Remember the goal is to get a matrix with ones on the diagonal and zeros everywhere else, right? That's the idea. And then these numbers would be our solution. But sometimes the system doesn't have a solution. Or sometimes the system has infinitely many solutions. And then what do we do with it? Well, what happens is those show up in the calculator as systems that the calculator just can't make it ones on the diagonal. Like it's literally impossible to make this matrix get into this format the way we need it. So the calculator does the best it can and gives us kind of the closest matrix. So this one ends up like this, something like that. And so we got to figure out what this means in terms of my solution. So what I always tell students to do is write it back as equations so that we can see what's happening. So for the first row we have 1x, 0 y's, minus 26z equals 0. For the second row, we have 0 x's, 1 y's, plus 8z equals 0. And then for the last row, we have 0 x's, 0 y's, and 0 z's. So we have 0 equals 1. That is our red flag. Obviously, 0 does not equal 1. That is a false statement, right? False. So because we ended up with an equation that is completely false, that means this system has no solution. There is no ordered triple that would make all three of these equations true, okay? And so we see that in our calculator as the calculator giving us a row that doesn't make sense. Okay, the row is false. 0 does not equal 1. So that would be a no solution. The other thing that we see is this matrix. If I do, again, the reduced row echelon form, and I'm going to use matrix B because that's where I typed example 2 is in matrix B. It reduces to this. So we have row 1 is 1, 0, negative 3, negative 5, 0, 1, negative 2, negative 7, and 0, 0, 0, 0. Okay? So this one, my third row, reduced to all zeros, as opposed to this one, which had that 1 at the end, right? So what does that mean? Well, if I translate this back to equations, just like we did before, I'll show you what we do with it. So we have x minus 3z equals negative 5, y minus 2z equals negative 7, and the last row I end up with 0 equals 0, which is true. 0 does equal 0, right? So because we end up with a true statement, that means there are infinitely many solutions. okay, because we end up with a true statement. Now, in this case, we can't just leave it as infinitely many solutions. We did that when it was equations in 2 variables, but when it's equations in 3 variables, we actually need to be a little more specific. So we do what's called writing our answer in terms of z. Okay, so we're going to have an ordered triple that uses just the variables z. Okay, so if I look at my equations here, the first one, I have x minus 3z equals negative 5. Right? X minus 3z equals negative 5. If I solve for x by adding 3z over, I get x equals 3z minus 5. If I take the second equation and solve for y, I get y equals 2z minus 7. So if you think about an ordered triple is normally x comma y comma z, well, I have an expression for x and an expression for y that uses the variable z. So x is going to be 3z minus 5. Whoops. 3z minus 5. Y is equal to 2z minus 7. Why do I keep doing that? And then z we're just going to leave as z. So this represents an ordered triple. Okay, this is an ordered triple that represents any of our solutions. So as long as the solution fits these expressions, as long as an ordered triple fits these expressions, then it is a solution. Okay, so for example, if I decided z equals 1, then I would have a 1 for z. I would have 2 times 1 minus 7. I would have negative 5 for y. And 3 times 1 minus 5 is negative 2. So that is one possible solution out of infinitely many solutions. And I figured it out just by picking a value for z. So any of my solutions I want, I could just pick a value for z, and that would give me one of the solutions. So in the problem on MyMathLab, we just want to type our answer in terms of z. So there are infinitely many solutions, and the solution set is 3z minus 5 for the x and 2z minus 7 for the y, and it already has z for z, saying where z is any real number. So this represents infinitely many solutions. Okay, infinitely many solutions. We're just being specific that the solutions have to fit these expressions. Right, so instead of just being very generic and saying infinitely many, we're being specific and saying infinitely many as long as they fit these expressions. Okay, when it's a no solution like this one was, that was back a couple questions. You just have to click that there is no solution. Okay? All right, well that's section 8.2. If you have any questions about your calculator or questions about how to write your results, let me know.